Welcome to our webinar here today. I am the editorial lead and I am here at IBM Research in Zurich, Switzerland. We've got a fantastic session for you today. We'll be talking about the first IBM quantum computer in Europe that is not in a research lab. So far, the IBM Quantum System 1 had only existed in IBM's New York-based data center. But now we have one in Europe. So here on the video, you can see this beautiful machine. It's got 27 qubits and it has just been unveiled in Germany for the Fraunhofer Institute. It was actually quite a spectacular event. Angela Merkel was there, lots of people, lots of journalists, lots of speeches. The video is online. You can go back and watch it. So before I introduce our guests here, I just want to invite all of you joining us here today to ask questions in the chat. I know people are joining us from all over the world and it's fantastic. Some people are joining from Russia. I know some from the US. Some people are even at a vineyard in Austria. So a special welcome to all of you. Do ask away. We've got a special team of scientists here behind the scenes. They will be answering your questions directly in YouTube chat. We'll try to get through as many questions as we possibly can. Some of them will be answered on air by our two guests here today. And they are my wonderful colleague, the lead of IBM, the quantum lead of IBM Research Europe, Heike Real. You may remember her actually from a previous webinar we had, I think back in February, when we talked about the future of quantum computing. If you don't remember or you didn't watch, please go back, find it because it was amazing. Hi, Heike. Thank you for joining us here today.
Hi, Katja.
And the second guest is Oliver Ambacher from Fraunhofer Institute. So he's joining us all the way from Germany. And Oliver is the head of the Fraunhofer Institute for Applied Solid-State Physics. Welcome, Oliver.
Hi, Katja.
Hi. So first question, actually, and as I said, yeah, for the people watching, do send us your questions. I will be asking our experts here every now and then the questions you guys are sending. But the first question, Oliver, is actually from me. How does it feel that now you guys have this fantastic machine actually physically in Germany at Fraunhofer Institute? Have you already started using it?
It's a pleasure to see the hardware and the infrastructure live and to have direct access to a quantum computer for the first time. We took over the administration to be part of the IBM QuantumNet and started checking the performance of the 1 and 2 qubit gates as well as the readout to check how the quantum computer can be good for in the future. And that was really already an astonishment highlight of my life, of my career, to have the machine here very close and started the operation of the machine together with Heike and a lot of famous people.
Wow, fantastic. So can you maybe describe a little bit, so what is the actual input and output of such a quantum computer? What does it look like?
I like to think in arrows pointing to a quantum state. Yeah. So by example, we started to mimic the formation of an ammonia molecule, something very simple where the electrons of the hydrogen atoms are interacting with the nitrogen atom in the midst. And you are looking for the optimal structure of the atoms forming the molecule. So every electron can be regarded as an arrow pointing to a certain electronic or energy state. And over time, you see if the programming is right, the algorithm is working, how the molecule is formed. And the output of the quantum computer is also a set of arrows pointing to the best position and energy state of the molecule. So it's a kind of first application, quantum chemistry, where you start with small ensembles of atoms, which can be mimicked by 5-6 qubits. And in the future, that can be enlarged to much more complicated quantum chemical reactions. And then this can become also interesting for industry.
Wow. Well, that sounds fascinating, and you've introduced quite a few interesting terms there that we're going to be repeating during the show today. And actually, it makes me think. I can see now already the first question has arrived from in the chat, and it's from Omrai. So I will ask you, Oliver, this question now, because I think it actually makes total sense in terms of what you were saying. He says, he or she, I'm sorry, Omrai, I'm not sure if it's a girl or boy, but they're saying, I'm currently in high school and interested in quantum computing, and I want to do research in it in future. So do I have to study quantum mechanics for it or not? What's your view on that, Oliver?
I would say it's strongly recommended. Just for programming, you don't need the understanding, the deep understanding of quantum mechanics is not necessary. But to understand how the hardware is working and where the potential and how it can be developed in the future, quantum mechanics is very helpful, and I recommend it. If there's a chance to learn it, do it. Beside quantum computing, it's an exciting scientific field.
Absolutely. I mean, I still remember Schrodinger's cat from my quantum physics course. That was fantastic. All right, so back to our fantastic new machine. And I guess question for you, Heike, what's the difference actually? Because here at IBM, we of course already have a quantum computer, right? And back when you and I talked in February, you were in the actual quantum computing lab that we can actually see now in the video. So what's the difference between that machine and the machine in Germany? And because IBM already built other quantum computers as well. So what's the difference?
Yeah, that's right, Katja. So we are building quantum computers, and we have quite a few already built. And so in general, the basic technology is the same for all of them. We are using superconducting qubits for all the machines we are building. And so although the machine in Germany has the same basic technology, and what you see actually behind me is one which is kind of a lab machine. It's more flexible. It's just what we saw in the video, which was disclosed or uncovered in the video. And it's a more flexible machine where we can, as researchers, test more, tune more things, etc. And the system, which is now actually also delivered to Germany, is the IBM Quantum System 1, which is engineered by our super engineers to be stable, to be reliable, to really for commercial, for continuous commercial use. And you see also that these systems are transitioning now from the lab, which we talked about before, and which you see in the picture behind me, or in the demonstrator behind me. And this machine is actually now sitting in a data center. So the machine in Germany is no longer in a physics laboratory, but is sitting in a normal data center. And that's really a transition. And for these systems are also engineered for.
Wow. So I have actually a question in the chat here. But before I go to that question, I mean, it just occurred to me just to mention that for all our viewers here, these machines, I'm sure many of you know, but to me, it just blows my mind. The temperature that the qubits are held at is lower than in the outer space. Okay, so I just wanted to mention that. Anyway, question from the chat: why is it so important to have the physical machine hands-on available in a specific continent or country? Somebody is asking here.
Okay, I mean, there are different reasons for that, right? And perhaps Oliver can jump into this also. But for Fraunhofer and for Germany, it was also very important that the calculations are kind of done in Europe, and that the data kind of is in Europe. And that was one point why the physical machine, why there was a preference for the physical machine to be in Germany. But in principle, for another similar machine also existed other places. And you can also, log in via the cloud and let your algorithm run on those machines. Mm-hmm. So the result will be the same. There shouldn't be a difference in the result whether it's run on the German machine or the US machine.
Good point. Good point. And as I like to say as well, science knows no borders, right? So that's very important. And the idea is, I guess, to finally reach what we call a quantum advantage, right? When these machines will finally kind of surpass classical computers in a specific task, correct?
Sorry, I couldn't hear you. Can you repeat? Sorry.
Yes, well, so the idea of all of these machines is to ultimately reach a quantum advantage, to surpass classical machines in a specific task, right?
Yeah, of course. I mean, that's really the goal, and that's why we are passionate for, right? I mean, we started to build quantum computers for really demonstrating the quantum advantage, which means to demonstrate the value of the machines to do calculations with a quantum computer, which a classical computer, a digital computer cannot do. And this for relevant problems, right? For really relevant problems in industry, which then provide also a commercial advantage compared to classical computers. And that's something which is really a goal we're driving for, and we developed the technology for that. And it's really right now a truly exciting time, because we feel that with a roadmap which we have built up, that we can reach this quantum advantage also very soon. And so here in the picture, you see actually the quantum development roadmap, which we have published last year, the hardware part actually at the bottom. And then in February this year, the entire roadmap, which includes not only the hardware, but also the software and the quantum applications part, and how we deliver then also service to the cloud. And of course, for demonstrating the quantum advantage, we have to further develop the technology, the software, but also the hardware, and how it all works together in the most efficient way. And that's what we're working on now. So if you see actually in this figure below, when you look at the hardware, then you see that we are continuously increasing the number of qubits from 27, which we have reached in 2019, but of course improved since then, although the quality of the qubits, because that's also very relevant, because we can, but also the number of qubits. So it's both of these things which need to be increased. So, and that's what we're doing. So today we have like 65 qubits, and this year we are going to demonstrate 127 qubits. And then also in the software stack, we are bringing in a lot of new capabilities for the different types of developers. So it's really an exciting mission we are on.
No, for sure, and that does sound pretty cool, I think. Well, a question for you, Oliver. I guess we are on a good way to quantum advantage. It seems to me. But what would you say is the role of System 1 specifically in this context? Like, why is it so exciting? I mean, Heike kind of mentioned it a little bit, but from your point of view, why is it so exciting for Europe and specifically for Germany to have Quantum System 1 at Fraunhofer today?
My experience was a little bit like the experience with my first car. First, I saw the car on pictures and I could understand from books how the motor is working, but I could not sit in the car and learn driving. And with the system in Eningen, the learning curve of the PhD student, which are now working with the computer, also the scientists, they have hand-on the system and they can learn to operate it. And that is a different quality. The learning curve is much steeper now than it was before. Also, we had already access to quantum computer in Yorktown by our cloud access, but the experience is completely different. So I would say to have access to the computer is a big step in education and probabilities to offer to students to deal with quantum computing. And another point is the cost for the quantum computer is relatively high. So in a couple of years, we have to justify the cost, and therefore we have to drive for applications. And a lot of companies in Germany and Europe, if they are dealing with the computers, they want to make sure that the data they are processing are safe in a way that they are not spread in other companies. So if you have your own computer, it's much easier to make safe that you are the one operating the computer and not another company. And therefore, besides education, to have a kind of data sovereignty in the processing with the help of the quantum computer is also something new to people in Germany and Europe, and is enabled by the IBM quantum computer in Eningen.
Yeah, no, for sure. I totally agree. And actually, on that, in that context, there is a question from the chat for you, Oliver. Somebody is asking, which institutions will access the quantum computer in Germany? What research topics will be at the core? There we go. That's a great question.
So the companies and university interested in quantum computer at the moment are most of or somehow related to physics and engineering. So the big university, Karlsruhe, Stuttgart, Konstanz, Munich, they are already on the way to use and sign the contract which is needed to use the quantum computing system in Eningen. And as far as I know, we have now already 14 universities which are close to access, and 26 which are associated industry partners associated to the first scientific projects running. And the first scientific projects running are dealing, as I said, with quantum chemistry, with optimization for product issues. Also, some of the universities are looking if they can develop algorithm which might help to make important infrastructure more resilient. So the students and the professors are very creative what a quantum computer could be good for in the future. And there's also a community forming, learning what the quantum computer can do and how the hardware can be improved so that the reliability of the results of the quantum computer is improved in the next couple of years in parallel to the roadmap which Heike showed, which is mainly related to increasing the number of qubits, which means we will be able to compute more complex systems. Beside the 27 qubits, the Eningen system is very robust for a quantum computer and has a quantum volume of 32. And Heike, I think we can say it. We are looking already forward to the next upgrade where we try to double the quantum volume to make the system, which can be calculated by people from industry and scientific organization, more fruitful. But in principle, everybody in Germany or everybody in Europe who is surviving, we call it export control, can have access to the system with our help.
Mm-hmm, mm-hmm. Wow,
so,
yeah.
Katja, if you don't mind, I want to interrupt and perhaps add to Oliver's point. Also, he mentioned that the great engagement he already has started with the industry and for learning. And also, I just want to mention that most of our systems, right, although the smaller ones are accessible for everyone through the cloud. And I have this high school student still in my mind, which you mentioned, because it's really exciting to have people joining very early and testing the quantum computers and using them also for learning. And of course, learning about quantum physics is not bad because it's a different thinking than in our classical world. And if you can then test this also with using quantum computers and check the result and learn how it behaves, it really helps you when you start very early on to generate kind of an intuition for these type of things. And I personally think then the earlier you start, the more you can generate this intuition and then also become more creative in your thinking and in your development. And I think, of course, for all of us, it's important that we have great minds coming to it and testing it and learning it and contributing to it, right? Advancing the field more. And so I really, want to encourage the student who asked the question to get started, to log into the systems, and also join the programs which we have, right? We have education modules, and also we have educators programs. Actually, if people want to use the quantum computers for education, then we are also to help and provide the access for the specific time, for example, they want to use it. So there are certain programs which people can make use of. And so, yeah, I encourage people to use it, right? Whether it's the one from in which it's sitting in Germany, or also the range of different ones from 5 qubit to 65 qubit, which we have available through the cloud. That's really something which can be used.
Yeah, fantastic. And I mean, what I would add to the high school student who asked the question is that they can even start programming video games on quantum computers, which is mind-blowing, I think. And we already do it. We're actually going to have a webinar just on that, hopefully at some point this year. But what Oliver mentioned, and you kind of referred to it a little bit as well, Heike, is kind of continuous development, continuous research, and also especially development of algorithms, right? Because I guess the more people around the world are using the computers and developing various different algorithms, all of that is helping the research, right? And eventually they will be added to like these quantum circuit libraries, similar to what we already have, for instance, with GitHub today, right? Is that how it will be, you think, Heike? Is that how you see kind of the near future?
Yeah, I want to give the example of, if you look at the semiconductor industry, right, and you go back like in 50 years ago, there was the first processor with 4,000 transistors, and this has to be programmed, right? And people had to work really at the very bottom, kind of to program the gates. And I think similar is a bit how we started like 5 years ago. You have to program the gates. But of course, then you really need to know a lot about the quantum computers. So we want to make it really frictionless for the developers, software developers, to use the quantum computers. So we have to develop the entire stack, which for the classical computers has been developed over the last 40, 50 years, now in short time frame, that many people can actually use these quantum computers. And so what you see here is that in the end, you kind of type in with the language you like, your program, you pick up your routines, they go via the cloud to the quantum computer. The process runs on the quantum computer, the result come back, and you get your result then on your classical computer. And so all this kind of, to make it easy to solve your mathematical problem by using the programs you use today, is kind of what we envision and what we're working on. And this is why we develop, of course, the hardware to demonstrate the quantum advantage soon, and then also to make it easy for people to program it. And perhaps I can go a bit, because on the quantum advantage, right, on the hardware development, Oliver mentioned it, there is the 27 qubit, which is sitting in Ehningen. Quantum volume is important. So we actually characterize it also in the quality, the capacity, and the variety. Because in the end, if you have a compute problem, you want to have it solved as quickly as possible. And this is actually what we want to implement also with the quantum computers. And that's why we, increase the number of qubits, because this, and not only the number of qubits, but also have them run very, very quickly through the cloud. And this means also the software stack is important. I don't want to go into detail, but the runtime is here very important for the ones who, who have a technical background. And so we have just recently developed also a Qiskit runtime, and have demonstrated that this was, with this combination, bringing the classical and the quantum computer closer together, that we can increase the speed by a factor of 120. Mm-hmm. So really a lot of things going on.
Yeah, sounds like that for sure. Somebody here in the chat, actually, I assume probably a developer, is asking, what can developers do with a high degree of understanding of Qiskit? Heike, probably for you.
So with a what they can do with a high degree of understanding Qiskit?
Yeah.
I mean, so contribute to the entire software stack, of course, right? Because we want to build it up from the bottom to the top, which means develop we kind of have 3 levels of developers in order to increase the abstraction from the hardware to the application in the end. So developing the kernel layer, but also developing then the tools in the algorithm development layer. And then this flows actually then in the model quantum application module developers. So as a user, you want to just kind of, use like quantum application models or quantum computing as a service. And this can be in the chemistry part, or it can be in the optimization part. And if you know Qiskit, right, then you can contribute, of course, to the entire stack, depending on the level of detail you want to go into.
Mm-hmm. Thank you. And Oliver, could you maybe tell us a little bit, again, going back to algorithms, about the role of algorithm development in companies and the need to kind of upskill companies and workforce development? What's your view on that?
Maybe I have to go one step back. By example, Qiskit for me is how the errors can be turned. And if you have 4 qubits and you have 4 lines in the Qiskit program, you are turning 4 errors at the same time, independent from each other or dependent from each other. And from this information, you have to subtract something which makes sense to the user. By example, now in my computer, when I'm talking to you, transistors are just switching on and off, and a clever gate made it somehow so that we can see each other. At the moment, we are just playing with quantum states, turning errors, and now we need algorithm programming so that there is a certain use for applications in the end. And that's not so easy. By example, that's why I mentioned quantum chemistry. That is a relatively small step to use the quantum state of a qubit to describe a quantum state of an electron. So that is relatively close. But by example, if you try to optimize the production line of a car production with a quantum computer, and you start from Qiskit and a couple of qubits describing quantum state, that is a very long way to go. And the steps we are now going with the first algorithm is somehow the step turning errors into something which can be useful. That's what I'm saying. And you should not forget, if you are switching on and off a transistor, you know there's current coming or not. If you are dealing with a quantum computer, the qubit says perhaps, yeah, so it's a kind of probability. So it's not always doing the same. So we have to do it 100 times, and if it's 90 times the same thing, which is coming out the same position of the arrow with a slight vibration, then we know with a certain probability this is the answer of the programming and the algorithm, and it's the result. Yeah, it's like a weather forecast. If it's 90% forecast for raining, you take your umbrella. But with 10%, you are taking the umbrella and you are walking through sunshine. And the quantum computer is talking to you in a similar way. It gives you a kind of probability. And that means a switch of thinking in your brain, which is needed to interact with the quantum computer, construct algorithm, which can be good for something in the future, for a certain application. It's still a long way to go, and the students are welcome to help that we can do it, because a lot of manpower is needed to check which kind of algorithm for which purposes can be successful.
Yeah, and I think that's also, Oliver, what Oliver mentioned is really also the point of if you have, in this case, for the algorithm development, you need kind of an understanding also of the quantum physics, right? That you can develop efficient algorithms which can be used.
Yeah, for sure. And actually, speaking of the basics of quantum physics, somebody is asking here in the chat again, maybe if we go back to you, Oliver, what is holding us back from having a large number of qubits? Is it fabrication-related challenge, or is it something more fundamental in physics?
Both, I would say. Maybe the students has heard of entanglement of quantum states. So the operation of a quantum computer needs qubits which are able to interact with each other. So they have to feel each other. By example, if the qubits would be made not of a superconductor like in the IBM quantum computer, it's made by electrons. The electrons are interacting by its magnetic fields. So they have to be very close, a couple of nanometer. And if you try to upscale a system where you need a very high precision of the production of the qubits, and then you have to control it, it's a technical challenge. So any qubit which I am aware of, if you would like to turn the errors independent from each other, you need the entanglement of the quantum states. It's a challenge technology-wise, and it's also a challenge to control the quantum states. And it's also a challenge to understand the results of the entanglement and the interaction of the qubits. And the more qubits you have, the more difficult is the control, because every qubit, in the ideal case, every qubit is talking to any other qubit. So the better you entangle all the qubits, the more quantum states are available for describing an application-related system. Mm-hmm. And therefore, the upscaling is not so easy. It's not just adding a few more superconducting circuits, and the system is upscaled to 2000 qubits.
Yeah, that's exactly the point what Oliver mentioned, right? It's not just, okay, you can build next to each other more qubits, that's no problem, but you need to be able to also control them well. And you need to be able also to increase their quality and reduce the error. And you have to solve their technical problems. And so when we look at our hardware technology roadmap, there are also for each of the generations where we scale up the number of qubits from one chip generation to the next one. And we actually have given them bird names, so you can nicely track them from the 27 qubit chip Falcon, then to the 127 qubit chip Eagle, and then to the Osprey with 433, and then end of 2023, we want to break the 1000 qubit barrier where we want to demonstrate Condor. And so from each generation to the next one, you have to kind of solve certain technical problems which are hard. And then they can be that we use, for example, you see these lines behind me, right? And also in your picture, Katja, which you have behind you, you have many lines coming down, right? You can imagine it's getting very dense if you go to 1000 qubits. So you have to think about what do I do in order to get rid of these lines to make them closer, to integrate them, or to make the qubits smaller when I go to 1000 qubits. There are many of those things which have to be developed and will be implemented. And with all of these, you have to further increase also the quality of the qubits and reduce the noise, that we come to this inflection point where we can then also do error correction, right? And these are all things that are still technical challenges, but we also have solutions which need to be implemented, and that's what we're working on. And so that's why when, for example, each 27 qubit chip is not the same, because it's the quality of the qubits also which make the quantum volume, and the entire system actually also makes the quantum volume. And that's what Oliver pointed out before. And so that's why we're also talking already about the next one, the next upgrade, which Oliver is already waiting for.
Yeah, at the moment we can run up to 200 quantum gates after each other in a fraction of a second. So that's the complexity of the program which we can enable with the Eningen system at the moment. That is nearly good enough for simple molecules. In principle, we are looking for quantum chemical reaction, and for that we need more qubits, but also a longer time where we can use the qubits in a reliable way to perform the program, to run the algorithms. And that is another challenge beside the number of qubits, the coherence time for the ensemble of qubits, which is limiting the time in which the quantum gates can be used to deal with a certain problem.
Mm-hmm. So basically, we've got a question actually in the chat here as well, but basically the quality of qubits is the longer they can stay in their quantum world, the longer they can do computations, right? And the question we have here from somebody in the audience, what is the relationship between quantum volume of a quantum computer and the number of qubits it has?
So then the quantum volume is kind of a complex set of parameters which let's put it this way. The quantum volume is one parameter which describes the complexity of the calculation you can do with a quantum computer, to say it in simple terms. And it's influenced by a number of parameters. So theoretically, it would be 2 to the power of n, where n is the number of qubits. But since there are errors, the fidelity is not ideal, and there's a certain coherence time, and there are also certain noise parameters, etc., and certain gates you can apply, and the connectivity of the system. So there are many things which are coming in, the way also how you lay out the qubits and all that stuff. And that influences then the quantum volume. And so that's why all these parameters which I mentioned are important to improve in parallel to get to a high quantum volume. So it's a number of qubits, but also all these quality parameters in addition, which make a high quantum volume.
Mm-hmm. Great, thank you. Well, maybe we go back to the machine in Germany for a second, and maybe we'll come back to basic quantum mechanics later. But what I really want to talk about right now, I know that when normally, like in normal times, if we didn't have the pandemic right now, the way to assemble a delicate machine like that in Germany, it probably wouldn't be that difficult because the team from IBM probably would fly in with all the components and just put it together. But I've heard that during the pandemic, it was quite a challenge, right? So Oliver, maybe you can tell us how it actually got assembled in Germany.
IBM did an excellent work and the system was available for us in time. Actually, what took the longest time was to get the glass for the nice design of the quantum computer in time from Italy. But very soon we realized that we have room for improvement of the system. So what was done a couple of weeks ago was to insert an additional Falcon processor into the system and add new amplifiers. That took a couple of days, but again, IBM was in time. We scheduled the 18th of June for operation of the improved system, and it worked out fine. So actually we survived already the first maintenance of the system with the result of improved operation.
But it was done remotely.
The pandemic,
remotely, wasn't it?
The pandemic was not able to stop us.
Perhaps I can add here also, as Oliver mentioned, it was not so easy to do all these things, right? Because we have a team who are the experts in assembling and deploying those systems. And actually, we have Chris Lirakis here also on the chat, who he's actually the lead of who led the team to build it up. And since, as you pointed out, they couldn't fly, they couldn't come to Germany and build it up together with a German team. It was a bit more complicated, right? And some colleagues had to get up very early, the ones who were sitting in New York, and work together with our German colleagues from the Böblingen lab to build the quantum computer up, to bring it also in time up, and of course to solve also things which are, you know, if you are at a site and you build up things, there are always things which come up and you have to solve. And I think they did really a great job. And I'm sure Chris can also provide further details on the chat about certain stories he may have encountered during that exciting story of building it up.
Yes, I think I heard one story when on Fridays the US team was drinking beer to celebrate the end of the day in Germany occasionally, right? When they got something right. I don't know if that's true, but anyway, so going back to the chat here, somebody is asking, once my company has a contract with Fraunhofer, do we get credits to access the system, or is it unlimited usage? And what will be the queuing time?
We have a kind of ticket system. So you buy a ticket and then you have 1 month's access per ticket. So if you buy 12 tickets, it's good for a year. The cost of a ticket is about 11,000 euro per month, approximately. And so you collect the work you have, and then you buy a ticket, and then you use the system so that you work it. We calculate the capacity of the system to be good for at least 100 to 120 companies at each time. At the moment, the queuing time is nearly zero. Mm-hmm. And Katja, maybe I can mention, if we have times of maintenance, which can happen, then we have a combined access to Yorktown. So we have a cloud access in combination with the Inningen system, so that in principle, the users have always the chance to work with the quantum computer. Most of the time with the system in Inningen, but if the system in Inningen would not be in operation, then we can add the cloud system.
Mm-hmm. And what about researchers outside of Fraunhofer and students as well? I suppose they can also access it, right?
Fraunhofer is only, I would say, a gatekeeper in combination with IBM. So if somebody is interested to use a quantum computer, we are only the contact and we help to make it happen. And because of the ticket system, we can shrink down the cost into packages where I would say every university or every professor or every small company should be able to afford it.
Right. And so I assume also, I mean, obviously we kind of talked about it a little bit before, but with students and researchers, the more researchers use it, it will also like help us move forward with the actual research and hopefully getting to quantum advantage at some point, right?
Yeah, but Katja, I don't know if we really need a quantum advantage. If I think, what is the best computer I had in my career? I had never the world best quantum computer or classical computer. You need the right computer for the right purpose. So I think it's not needed to have the fastest computer on the world. It must be the right system for the application. So what we are looking for, what are the potential applications for quantum computing or hybrid system? And we try to optimize the algorithm and the hardware toward this application. For prestige, I'm sure IBM should have the best quantum computer on the world, yeah, which is also overcoming the potential of the best classical computer. But I think the real world is the combination of classical, as Heike already said, and the right quantum computing module, which is optimized for the user. And therefore, I think there will be not the one computer, at least not the one system, like in the classical, where all the adaptation is done by software. I think we will face a bunch of quantum computer system in the next 10 years. Maybe later on, there will be one who can do it all. But I think in the next couple of years, it will be not the one system.
Right. Thank you. Heike, what's your view on that?
Yeah, I think, of course, as you pointed out, right, I think quantum advantage, how we define it, that it's the advantage, demonstrating the advantage of a quantum computer compared to a classical computer, that you can solve a certain problem in a more effective way than a classical computer. This is the advantage we all thrive for, right? Because otherwise we could use classical computers. And that's of course the goal. And this has to be done for a relevant problem, not just a toy problem. So that's what we want to demonstrate, this for a valuable, relevant problem, which provides then in a certain industry, a certain company, or also scientific problems. Certain scientific problems cannot be solved by classical computers, right? And if we can solve some, then also with a quantum computer, then we have a true advantage. And that's what we want to demonstrate, right? And of course, there's also a path or a roadmap of those problems, because some of them may be easier to reach than others. And that's what what we are working on, also together, of course, with the partners.
Yeah. Speaking of partners, actually, what would you say actually is the importance of this momentum that's been created by bringing Quantum System One to Europe, to Germany, from the point of view of research, of course, but from the point of view, as you said, partners and other companies who work together with you at Fraunhofer?
I would say awareness. Students are now interested to work with the system. Companies try to set a foot in the door to learn what a quantum computer can do. The politicians are pumping money into the system to make it happen. So I think it's a big push. So I think the community was waiting for it and is ready for it. And now we get a real wave. And now we are responsible that this wave will end in something which is useful for all day life, at least in a couple of years.
Great. Well, actually, now I'm reminded here of questions that arrived before the session started through Twitter and other social media networks. So here is a question for Heike. If I run an experiment on the current 27 qubit system, and then again on 65 qubits, and eventually 100 and 1,000 in a few years, what will change? Will it be faster results or better accuracy?
Yeah, so as we kind of pointed out through the discussion already a bit, right? The quantum volume or is important, that you can increase the complexity of the calculation you can do with time, and thus also reach the quantum advantage. And so therefore, it's the number of qubits which is important, but it's not everything, because a computer with, for example, 65 qubits can have also a lower quantum volume if it's not the same quality of qubits than, for example, 27 qubit. And so we really have to increase the number of qubits, but also the quality of the qubits in order to increase the complexity of the calculations which we can do. And so you have to look into detail, but of course you look for the best quality, capacity, and in the end also variety of the quantum circuits you can have.
Question for Oliver here from the chat, and you may have answered it already. If you have, maybe you can just reiterate. Is it possible to rent access per hour or per day?
No, that the administration would be just too high and too expensive. Therefore, we said the minimum is months.
Right. Okay. And now I can see another question that actually arrived before the session, a fun one for maybe both of you, or maybe one of you can take it. If I demonstrate a quantum advantage on Quantum System 1 in Germany, can I get one of those cool quantum models that Chancellor Merkel had in the live stream?
Yeah, you can have it.
Yes.
I have a few to share.
Fantastic. So whoever asked the question, please go ahead and do demonstrate quantum advantage. The sooner, the better, and you'll get one of those models from Oliver. Great. Okay, now on a more serious note here, a question from Graham in the chat. I would like to ask Heike where she would see the biggest advantage for quantum computing. Where do you see the best environment or business where quantum technologies can be used?
So when we talk about, so there's quantum computers and there's quantum technologies, right? Quantum technologies can also be sensors and other things which make use of the effects of quantum physics, and in particular also entanglement. We speak mostly about, of course, the quantum computing world. And here I indicated before that there are many problems which classical computers cannot solve. As physicists, we find approximations for these things, and some of these approximations work well. For some other cases, they don't work well. I mean, a simple example, we did not yet find a material where we could, for example, reach high temperature superconductivity under ambient conditions. And those problems, obviously, we cannot calculate them well enough in order to find the right material. And that's one example. And so quantum computers in that respect could really help. And so there is kind of a roadmap for those problems, which actually is currently also need to be developed. And I think that if you look at the quantum chemistry part, Oliver mentioned it, that the 27 qubit, which is in aiming and could work with smaller molecules, right? And with the increase in quantum volume, we can go to, for example, higher or bigger molecules and can calculate those. And then you can reach at a certain point and also bigger problems like optimization problems where you may need bigger quantum computers and also error correction. So it's really a roadmap which we have to develop.
Actually, I would ask Oliver the same question as well. What's your take on that, Oliver? Like, where do you see the biggest advantage for quantum computing?
I'm on the same trip like Heike. I think quantum chemistry is the closest, because we can also benchmark systems by simulating simple chemical reaction. And in the future, I think it should be possible to develop medicines. So it can be interesting for big chemical companies, but it can also help, let's say, in pandemic challenges, because you have to develop something new in a very short time, which is really complex. And that are typical tasks which can be solved with the help of quantum computers. But
yeah,
that's a good point.
Yeah, Oliver, I think you really make a good point. And I think we should, for those types of problems, of course, we also look not only on one computer, right? Because we want to make use of the entire technology which we have available. And so in particular for those things, we want to create like an accelerated discovery mode where we can solve those problems much faster and combine like the HPC delivered through the cloud with quantum computers, and also make use of AI. So it's really a complex problems. You also have to apply all the technical capabilities you have. And so that's something which we, for example, also recently announced where we collaborate also with Cleveland Clinic in order to go exactly for those healthcare and life sciences problems by making use of big data, applying the different compute technologies for medical development.
Mm-hmm. And what about, for example, space exploration? Do you think quantum computers would be useful for that in terms of maybe calculating the best route to get from us to, I don't know, even to Mars or elsewhere?
Maybe not to Mars. By example, we have 300,000 trucks in Germany, and half of the time they are driving completely empty because the navigation system and the logistics of the trucks is they're doing nothing. So in principle, what a quantum computer could do is an energy optimized navigation of all these trucks, including the loading of the trucks. And if you think about that, even the small trucks are consuming 40 liters of fuel each 100 kilometers, and they are driving 2 billion kilometers each year. That is also an important saving of our environment. So all these kind of optimization problems with a lot of states, a lot of cars, a lot of trucks, that is again a challenge which can be solved with the help of quantum computers. Mm-hmm. Maybe we have not to ask for the Mars, maybe we can deal with the all-day problems first.
So, Oliver, I like your take on this, because I also think we have enough very critical and important problems for the society and mankind to solve on Earth. So I think the example you gave is really one good example, and there are many of others. Like if you look at the applying quantum computing, for example, for the nitrogenase, for the generation of food, and so I think there's a lot of interesting, complex problems we can solve here.
And maybe one can add, I'm not sure, but there's a chance if we can do information data processing with quantum states with the smallest amount of energy possible. I think there's also a chance to provide computing system using by themselves a much lower amount of energy, because a high power computer needs 700 amps. So the amount of electrical power which is needed and cooling is very high. I'm not sure yet, because a quantum computer needs also a lot of cooling. But if it's once cold, then I think it can be operated with a small amount of energy. So we can at least check if quantum computer could be the more energy saving information processing.
Mm-hmm. Yeah. Actually, I think Oliver, that's a very good point. I can elaborate a bit on that, because if you look at the energy efficiency and compare it, and that's something which is of course also still part of the research, but is already first initial research coming out where you compare these systems, and if you compare like an HPC, a high performance computer with a quantum computer. And then a quantum computer, I mean, it really needs a factor of thousands lower energy, and can solve problems which, in the future, that's a target which HPCs cannot solve. So energy efficiency is definitely also something which is on our mind. And so I think it's exciting things to come.
Absolutely. I think we have just about enough time for the last two questions here from the chat. So somebody is asking, regarding possible use cases, would it be possible soon to calculate how airplanes could find their ideal flight way to the airport to never be late?
Yeah, that's similar to the optimization problem of the trucks. Yeah, the question and the algorithm and the program is very similar. So all this optimization of complex logistic systems, packages, trains, cars, I think that is one way of thinking where quantum computer system could be optimized too. But as Heike and me pointed out already, we have to increase the number of qubits, we have to increase the coherence time, we have to decrease the error rate of the system, because if we are dealing with airplanes, we have to make sure that the information provided of the quantum computer is treated in the right way. Because if not, then it's dangerous. And therefore, I think we should start with the quantum chemistry and deal with the atoms first and learn the optimization problem. And if that's working, we can go to more complex and systems which should be more resilient and where human beings are involved.
Mm-hmm. And so, actually, Oliver, what you mentioned is you show again the roadmap, right, and that the technology has to evolve. But as you also point out, we already can think now of assuming that the technology is coming, right? What are the problems we can solve, and also developing the corresponding algorithms. And in that regard, I want to, for example, also highlight work which we are doing also on like exploring this space and also exploring the physics in space, right? When you look at CERN, there are many there are big problems. You have big data collisions, like particle collisions, and you want to calculate these problems and use also machine learning and other stuff for it. And that's really complicated problems where quantum computers can help in the future. And there are bigger systems built. There's more compute power needed. And that's also something like Katja, right? We will talk more about this in the future in one of those webinars.
Absolutely,
and we should not forget, we have maybe 50 to 70 quantum computers on the whole world up to now, and maybe IBM has half of it. So the whole capacity is still very low. So we have to increase the number of hardware and the quality of the hardware that we can develop and attack all these challenges in a decent time.
That's absolutely right. And so the very last question for you guys, what would Albert Einstein have asked if he could have attended the session? Somebody is asking in the chat.
I think he would ask if we can find out the quantum nature of gravity waves.
That's a good point. All right. Well, fantastic. Thank you so much, everyone, for being here with us today. Thank you, Heike and Oliver, and thank you to all the scientists here answering questions in the chat. I'm sure there were many, many more questions than we were able to answer on air. As always, stay tuned for the next webinar next month. And if you have any ideas, questions, comments, feel free to send me a direct message on Twitter. It's SciTechCat. And also don't forget to subscribe to our channel if you haven't already. See you next time. Thank you and goodbye.
See you.
Bye-bye, everyone.
Bye.
See you. Thank you.